start recording. And share the screen. So I'm not going to review the whole thing. We talked about the kinetic energy of rigid bodies. If they have translation, is like a particle. We saw before translation kind of looks like particle because every part of that rigid body moves same way. For rotation, we get this, and for general motion, a combination of translation and rotation. Then we talked about work of a couple. If it translates, no work, but if rotates, you're going to have m d theta. You integrate moment or couple over the angular displacement and you get the work. Remember, the unit for work is joule. Now it doesn't matter, it's the force displacement and moment times theta, the unit is going to be the same. Then we talked about conservation of energy, relation of work and energy, and all of that. Everything is the same, except when you calculate the work, you have to consider the work of couple and force. When you calculate kinetic energy, the component representing translation and the component representing rotation. Okay. And then if there's no work, conservation of energy. And we also briefly talk about that if you have a rolling object and there's a static friction, the static friction does not work because static friction, the name says a static, doesn't move, right? So these are the things we talked about. Of course, we did one example here, calculating kinetic energy of a mechanism completely. We had to use IC, which was easier to use, right, compared to like vector analysis to find all the components. Now we're going to do another example. By the way, before we start, Aaron, the students in the class, I think you have seen him asking questions in the things, right? Anyone knows Aaron? He missed the lecture yesterday on Monday because he is on duty, and asked someone send him the lecture notes. Any one of you would be kind, how many of you would take notes, or how many of you just, you know, use the slides? If anyone takes note, could you send those notes to Aaron? Can anyone take the responsibility to do this? Anyone? You don't care, right? Anyone takes notes here? Come on, guys. I'm not asking technical question.
I could do it, but I take my notes on an iPad with the slides, so I don't know if that is.
I think that should be fine because he probably has the slides because I posted, right? And if you need his email address, I can send his email address to you after the class, okay? And he missed the lecture today. I think he's going to miss the rest of the semester. We talked about this. He's like an active military person, so he's excused. But to help him understand what's happening here, he could watch the videos, but sometimes having the notes is useful. So I'm going to send you his email address. And if you can send all of the notes from now, I appreciate that. Is it okay? Okay, good.
Yeah.
So now with all of this, we're going to do this example. This is a good example that almost has everything. You have a spring here. This disc is going to roll on this surface. That means its elevation changes, goes up and down. It has a moment, a couple, which is external force. We have to calculate the work of this couple. And it has another thing that says the spring holds this disc. If you read the problem, it says the disc is originally at rest. Remember, if there was no spring, this could roll down and go, right? So when this is at rest, that means this spring holds it. So that means this spring creates some force and has initial deformation. It's not like neutral, you know, size. It has some stretch in it. Now, it is at rest. We apply the moment of 30 Newton meter. And obviously this will start moving, gain some velocity, then the spring stretches further until it's going to stop. We want to know how far it goes before this stops. And it says the disk rolls without slipping, which means here we have a static friction. And we just talked about how the work of static friction is calculated, right, Colin? How much is the work of static friction here?
0.
0, because it's static, it's not moving. Okay. Let's go to the tablet. This is how the problem looks like. Now, please pay attention here. This is position 1. Let's just call this position 1. Okay? What happens when this rolls down and stops? The disk is going to move somewhere like here. Let me just extend this line. Okay, so the disk is going to move somewhere here and it stops. Okay, this is the distance. Let's call it D. The distance is going to go before it stops. So is the physics of the problem clear? There's one more thing. If you look at the equilibrium of the disk, if I do the free body diagram, so this is for a static case, static equilibrium at point 1. If I do the free body diagram, this is the disk. You're going to have mg. You're going to have normal force. And you're going to have the force of spring, right? Do you have any other force? It's sitting there. It doesn't try to move, so friction doesn't get involved. If you consider this, I'm going to divide, obviously, mg into these components, right? Then you're going to get, so this is for a static equilibrium again. You're going to get, let's say this is x, or maybe the other way, doesn't matter, because it's 0 anyway. This is x, this is y, summation of forces in x0, and that's going to give you fk minus mg sine theta is 0. This is same theta as here. Okay, and summation of forces in y equals 0. It gives you n minus mg cosine theta 0. The second one, we don't care. This gives you n equals mg cosine theta. But the first one, Fk, which is K times x1, the initial deformation of the spring is going to be equal to mg sine theta. And from here, you can find your x1 as mg sine theta divided by k. Let's just calculate the number here. M is 20 kilogram, 9.81 sine 30, and your k is 150. How much is this number? .654 meter, right? You guys get the same number? So I did the static part just to find out my x1, because I need this in my energy equation. Okay? Any question? This is like a simple problem from the static course. You have just a spring holding a disk, 2 forces, 3 forces, you just add them up and get that thing. Now, let's move this down so I can continue with this. And let's say we go from position 1 to position 2. Obviously, I'm going to use work energy method. What is the equation I'm going to use? The equation I'm going to use is principle of work and energy. That means summation of T1 plus summation of plus V1 plus summation of U12 non-conservative is summation of T2 plus summation of V2, right? This is the overall equation. Any question about this equation? This is just a straight from the notes, right? Now, the problem says the disk is originally at rest. So T1 is 0. And it says find the distance d when the disk stops momentarily. What momentarily means it rolls and it stops for a second. When it stops for a second, how much is its velocity? 0 again. So you get summation of T2 equals 0, right? Summation of V1. For V1, we have 2 components. One is gravitational potential energy. One is spring potential energy. For spring, we determine how much original deformation is. So you're going to have half K x1 squared. How about gravitational potential energy? How do we find that? Andrew, how we find gravitational potential energy at 1?
It's the mg cosine of 30 degrees.
Mg cosine of the... How did you calculate that?
Because it's on a slope, so it's cosine. Because if it wasn't, it was just mass times gravity.
So Mg is potential energy.
Yes.
Mg is force, right? Is weight.
Oh, It would be height times gravity and
Height times gravitational force, correct. But
yes.
we need one step before this. And that's why the reason I ask. You have to have a reference point to measure your height, right?
Mm-hmm.
Usually we have some flat level or whatever you can use, but I told you before, it's completely arbitrary. To make the life easy, I'm going to choose the lowest position of the disk, center of mass. I'm going to use this as my reference for y, okay? Now, if this is the distance between the two, this is going to be y1. And because this angle is 30, first of all, it's sine, it's not cosine, but you got the idea, right? So if that's the case, you're going to get plus mgh or y1, which is d times sine 30, right? So we're going to get d sine 30. This is the initial potential energy. Looks good? How about final potential energy? Your spring further stretches, right? So you're going to get half k x2 squared. I'm just going to call it x2, the final deformation of the spring, and we're going to find out how much it is. How about the gravitational potential energy? When the disk is here, how much is its y based on my reference? It's going to be 0, right? Because technically that is the point we chose, so it makes life easier. Then we're going to find the work of non-conservative forces. And when we say forces, it's a generalized force, moment, couple, everything, right? What is the non-conservative force or moment here for couple? Do we have any, by the way? Chris, do we have any non-conservative force or couple?
The moment.
Yeah, this guy here is an external couple, and I told you all external forces that you apply, push, pull by hand, by something, by electromotive or whatever, those are non-conservative. So if that's the case, it's going to be, and m is constant, so integration of m d theta is simply m delta theta. The question is, how much is this delta theta? Let me put all the parameters in the equation first. You have this, oops. You have this guy, this guy, this guy, and this guy, right? I'm going to substitute in the main equation to make the life easy, and then we're going to go find one by one. So on the left-hand side, you have half k x1 squared plus mgd sine 30 plus m delta theta equals the right-hand side, which is half k x2 squared. Okay? Looks good? Now, x1, we calculated. D, I don't know it. Delta theta, I don't know it. X2, I don't know it. So we have 3 unknowns. And remember, this is a scalar equation. You cannot have 3 unknowns. How we're going to relate these things together? Look at this geometry. Suppose that let me give you a second to write down this, and then I'm going to explain on the. Anyone can suggest how we can find extra equations to find like d or theta. Technically, d is the final output of the problem, so we're going to keep it. Anyone knows how I can find x2 or delta theta in terms of d? Anyone? Yang?
Wouldn't delta theta be S or D times R?
B times R. Good observation. Look at here. If this is your disk and goes here with the distance D, distance D is going to be an arc here, right? To roll over this arc, and these are the same. And if you calculate that arc in terms of things, this is theta. So technically D is R delta theta, or your delta theta is D over R. So we got this one. Okay. Delta theta is D over R. How about x2? I'm going to erase this. If you need to look at it, you can watch the video later because I want to keep this part clean and continue. How about x2? Look at here. Let's say this is, oops. Let's say this is the neutral length of a spring, like x equals 0. You had your x1 here, and this is going to be your x2, right? The final length, which is going to be like this, minus neutral length. How you get that? Your x2 is what? Is technically this, which is x1 plus this. So the initial displacement is x1. In a simple English, you add d to it, right? So if that's the case, let me clean this thing. Then if that's the case, you're going to get x2 is going to be x1 plus d. Now I have everything in terms of d. I'm going to substitute these values, half k x1 squared plus mg sine 30 times d plus m. I'm going to substitute delta theta from here over r times d equals half k d plus x1 squared, right? If you expand this and simplify, and I can substitute the numbers, half times 150 times 0.654 square plus, I'm going to factor d here. Look at here. I'm going to factor d here. So we're going to get mg2 times 981 sine 30 plus m, which was, how much was m? 30 divided by 2. This is going to get times d. And on the right hand side, half times or 150. Now you're going to get d squared plus 2dx1 plus x1 squared. So if I expand this side, you're going to get half 150 d squared plus half 150 2d times x1 plus half 150, and let's just substitute as x1 here. You see, I have half 150.654 square, half 154.614 square. So I can cancel out this at the two sides. You even don't have to calculate it, right? So you can see we're going to develop a quadratic equation, right? So let me calculate all of these parameters, get the numbers. So this goes to a simple shape. This part, $9.81 plus 15. We're going to get 24.84D is equal to 75D squared. This part, we're going to get 0.654 times 150. And this cancels this two. So you're going to get plus 98.1 D. And we get rid of this term. So that's it. So it makes it easy. Okay. Now I transfer everything to one side. 75 D squared plus 98.1 minus 2484 D equals 0. And this $75 D squared plus 73.26 D equals 0. How we solve this problem? Did we get everything right here? So if you factor D, you're going to get D times 75D plus 73.26 should be 0. I think we missed a negative sign somewhere because D should not be negative. Let me double check. mg sine theta. Oh, hold on. The mass of this guy is 20. Okay, now I see. Guys, I made a mistake here. Let me just fix this. This should be 20, but I think I got the final number right. So 20 times 9.81 times 0.5 plus 15. Okay, this term, I got it wrong. This term, let me fix it here. It's going to be 113. I put 2 for mass, it was 20. This term that comes here, the mass was 20. Now, if you consider that, we're going to erase this and substitute the value. And then this becomes 15, the difference between the two. Then this becomes minus 15. Okay. The mistake was here. I put 2 instead of 20. The mass is 20 kilogram. Now you get D equals 0, or D equals 15 by 75, which is 0.2 meter. Which solution we choose? Because quadratic equation always have two solutions. Usually one of them is meaningful, the other one is not meaningful. For example, if I get like negative number for a distance, negative or time, it's not acceptable. But you see here, D0 is a legitimate number and 0.2 is also a legitimate number. How we interpret this? And you should look at the definition of the problem. Look at here for a second, please, everybody. The problem says in position 1, V is 0, and the final also V is 0. So interestingly, when you get D equals 0, refers to this, D equals 0.2 refers to this. So one solution shows the initial point, D0 is when you have 0 velocity. One solution shows the final position when you have V0 and D is 0.2. But what we are looking for is after displacement, so D is 0.2. Any question about this? I think this problem has some interesting parts. I'm going to count them, right? First, using static equilibrium to find x1, okay? That is something now you learn from now. If there's a static equilibrium, you balance the forces, you find how much springs the forms. 2, displacement, let's call it linear displacement. Linear displacement D and angular displacement delta theta are related. Why? Because the disk is rolling and you get D is R delta theta. Okay, so next time you see something like this, you're going to use it. If something rolls, the displacement of the center of the disk and angular displacement delta theta are related like this. So the other one was initial at rest and final point temporary stops it means T1 and T2 are 0. We have seen this before when it says start from rest, no velocity. When it says temporary stops at the end, also no velocity. The rest was just finding the values, right? The other thing that you should consider always, and this is something we talked and examined before, a reference line for elevation, right? It could be any point. In this case, that it goes from here to here, I pick the bottom point as my Y. You could pick the top point as your Y, then your second potential energy will be negative because it's below reference, but whichever you like, you can do that. These are few things we practice here, and we go from there, right? The rest was just writing this equation. Where is it? Writing this equation, finding the terms, and solving for the unknowns. The other thing was, okay, you can add that final deformation of a spring, and this is always the case, right? Is initial deformation plus secondary displacement, whatever you name it, plus extra displacement between 1 and 2, position 1 and 2. So which was like x2 is x1 plus d. Now, sometimes you may have sine cosine because there's an angle involved, but if there's an initial displacement, geometry tells you how much the final deformations and displacement are, you just manage them like that. Any question about this? Can you do it in a quiz on Monday? No, we don't have Monday quiz for this. Final exam, maybe. Yes, no? Okay, let's go back to the slides. We're going to solve this problem. Okay. This has pound units and stuff, pound and feet, so it might be slightly different. So you have a slender rod here is horizontal at this position. At the end is attached to a spring, and a spring has a roller here. This roller allows that as this rotates, this roller moves back and forth, which means the spring always remains vertical. That's the meaning of this geometry. It says spring has an unstretched length of 2 feet. Look at here, everybody. The unstretched length is 2 feet. The length here is 4 feet. How much is its deformation right now? Come on, guys.
2 feet.
2 feet, right? 4 minus 2, 2. So the initial deformation at this position is 2 feet. That's the x1. The stiffness of the spring is given. This has initial velocity, is not released from rest. If the problem says this is released from rest, then all kinetic energy values are 0, but because this rotates, it has kinetic energy. The problem asks determine the angular velocity of the bar when it rotates 30-degree clockwise, so goes down 30 degrees, okay? Let's draw this and see how it goes. So the end of the spring is attached to the roller. As I said, this means as this Slender rod rotates, roller moves back and forth, and keeps the sky 30 degree, sorry, perpendicular. Any suggestion how to solve this problem? So let's switch to the tablet. This is how the problem looks like. So let me see the values. You have an omega 1. I'm going to put all the values. So this L, let's say L is 6 feet. Theta is 30 that I wrote there. Omega 1 is 2 radian per second. The weight of the bar is 50, so W is 50 pounds. And X1 is 2 feet. K is 6 pounds per feet. And L0 for the spring is 2 feet. Right? Because we need L0 to find X2. Yeah, this is how the system looks like. As I said, because it rolls, allows to this to be perpendicular all the time. Any suggestion how to do this? Come on, guys. Give me something to start. This could be in the exam.
Did you use the kinetic energy equation that's like 1/2 I omega squared?
Well, good start. We don't have kinetic energy equation. We have conservation of energy equation, right? I mean, kinetic energy is a part of that, but because there's no non-conservative force, all we have here is technically, if this is center of gravity, right? The center of gravity is going to go like here. Right? And we have a spring that is here and goes here, and that's it. So to solve this, we can start with, there is no non-conservative force or moment, obviously, couple or anything. So I can write summation of T1 plus V1 is going to remain the same. And this is the conservation of energy, right? Now, how much is T1? We have, you see, we always use the summation because there could be more than one object, but here, technically, I have just this bar. Okay, that's all I have. So I have one object. If that's the case, how much is T1? This object here, what kind of motion it has? Guys, you need to be quick here. If you know it, just say it because it makes me worried when you pause. Rotates about fixed point, right? Yeah. So when it rotates about fixed point, how do I find its kinetic energy? Let's call this point as O. Rotation about fixed point, the kinetic energy is half I-O omega 1 squared. Right? The final kinetic energy is the same thing. It's going to rotate with omega 2 here. Again, rotates about fixed point. So that's the same. And if that's the case, we're going to get half I about O omega 2 squared. Any question about this part? Now, we go to potential energy. We have gravitational potential energy because this rod rotates up and down, right? The G goes down, so we have gravitational potential energy. We also have gravitational, spring potential energy. I'm going to start with the spring. We know that originally we have some deformation. The problem says how much it is. So we're going to get half K x1 squared. For potential energy, what do I need before I measure any value?
Reference point.
Reference point. Which point you pick as reference? Usually you can pick one of the points, one of the 2 points as your reference. You can put this as your Y, or you can put this as your reference for Y. It doesn't really make any difference, but to me, it kind of looks nicer if I pick the first one, right? So if this is the reference for potential, gravitational potential energy, your Y1 is going to be 0, right? So you simply get plus 0, and this is for mgy1. Okay. The final potential energy, your spring stretches further here. This is spring, right? You're going to get half K x2 squared. And now you have this height as y2. How much is it? This height or this height? How much is it?
3 sine 30.
3, which is L by 2, half of L, because this is symmetric. This is L by 2. So I'm just going to keep it L by 2 so we know where this comes from, okay? So we're going to get M G L by 2 sine 30, right? And that is going to be this height or this Y2. Any question about this? So I found all the terms I need. I'm going to substitute into this equation. And if I do that, I'm going to get half. Let me also, you know what? I'm going to write it down and calculate IO. Half IO omega 1 squared plus half K x1 squared equals half IO omega 2 squared plus half K x2 squared plus mg L by 2 sine 30. Omega 2 is something we are looking for, right? I think that was the thing. Let me see. It says determine the final the angular velocity. Yes, that's what we're looking for. So how about x2? How much is x2? Look at this geometry. This is your L1. This is your L2. The difference between these two, which is this guy, the difference should be added to x1, right? Because up to here, it had x1. Now you go this much more. You guys follow? So your x2, let's call this as h2 or h. Oops. I'm going to call this height as h. So x2 is technically x1 plus h. And from this geometry, this h is going to be the whole length of L times sine 30. Okay? So if that's the case, it's going to be x1 plus L sine 30. Now let's just calculate that. This was 2 plus 6 times 0.5. It's going to be 5 feet. So I found this, so this is good. This is good. I also need to find I about O. Moment of inertia of a slender rod. This is the slender rod. Moment of inertia about here. Do you guys remember? We had in the textbook. So IO is going to be M L squared by 3. And M is going to be W by 32.2. Because everything is in pound. W is how much? 50. So 50 divided by 32.2. One, 5, 5, 3 slug. If I put 1.553 divided by 3, remember, this should be in feet. Sometimes it gives in inches. Now it's already in feet. 6 square times 6 square, then divided by 3. So this is going to be 18.634. The unit slug feet square. So I got this guy. I got this guy. I'm just going to plug all the numbers and give you the final answer. So you're going to get here half times 18.634. Omega 1 was how much? 2 square plus half times 6 times 2 square is equal to half 18.634. I'm writing this part. Omega 2 square plus half 6 times 5 square. This is this term. And then plus mg, which was 50 times L by 2, which is 3. Let's just put 6 by 2 so we know what is what. Sine 30. So you see in this equation, the only unknown is omega squared. I'm going to let you calculate this, give you a minute to do all the things here, and just write the final answer. So your omega 2 will be 2.3 radian per second. And please calculate and check if you get the same number, or maybe you have done some mistakes somewhere. Did you guys get the same number?
I am not getting the same number. I'm getting like a negative number before you would like take the square root.
The negative is not definitely right. Let me see if we got something wrong here. Oh, okay. Good observation. Good observation. Hold on. I made a very big mistake. This mg, this kinetic energy, remember, this is my reference, right? When I go below the reference, it should be negative. Thanks for catching that. This should be negative because technically your L2, this term, your Y2 is smaller than 0, is negative. If you keep this negative and make it here negative and put it here as negative, then you should get a positive number.
Also, I think that should be 50 divided by 32.2.
This is weight already. You see, this is mg. Mg is weight, so you can put 50. That's okay. But in calculation of I, this, you have to go with the slug. If you put that number, I think you should get that. I'm glad you find the thing here. Yeah, when you go below the reference line, it's going to be negative. When you go above the line, it's going to be positive. Okay. Now, let's do one more problem. Do you guys want like 5 minutes of break? Okay. Let's come back at 11:03 or 4, something like that. You know what? Make it 11:05. And then we're going to continue with another example. Okay, let's continue with another problem. So in this problem, as you see, you have a disk. So your rigid body has a little complicated shape, which means you want to find moment of inertia, you have to find moment of inertia for all of this. This is a disk with a weight of 15 pounds. You have a 1 foot rod with a weight of 2 pounds and a sphere of 1 foot diameter, which is 10 pounds. There are welded connected as one piece, one rigid body. And it says the spring is originally stretched 1 foot. So your X1 simple is given. Your X1 is 1 foot. And it says sphere is released from position shown. So when it says released, again, it means no velocity. So initial velocity of the whole system is 0. Initial stretch in the spring is given. You release this. Obviously, this is going to rotate, going down. The problem says find the angular velocity of the system. It says this was, remember, everything is joined together, welded. Angular velocity of this rigid body when it rotates 90 degrees, which means this sphere goes down here. Okay. All the numbers are given, the dimensions and everything. So let's go to the tablet. So this is your disk. This is your rod. And this is your sphere. The dimensions, let's call this as R sphere and call this as R disk. And I'm going to call this just L, the length of the thing, okay? The spring here is stretched by 1 foot. So K is given, and I'm going to write all the numbers. So I use D for disk, R for rod, or like capital R. Let's just do everything capital, doesn't matter. Rod. And S for a sphere, okay? So W of disk is 15 pounds. I'm going to find the mass of disk, 15 by 32.2. W of rod is 2 pounds, which means mass of rod is going to be 2 divided by 32.2. W of a sphere is 10 pounds. Mass of a sphere is going to be 10 divided by 32.2. So also the L is 1 foot. The radius of a sphere, RS, is 0.5 foot. And the radius of disk is 2 feet. Okay. K for the spring is 4 pounds per feet. And X1, it just simply gives you 1 foot. So this is all the information you need. Let me calculate these numbers for the mass. So 15 divided by 32.2, 0.466 slug. 2 divided by 32.2, 0.062 slug. And 10 divided by 32.2, 0.311. Okay. So let me highlight the numbers that we need. This guy, this guy, this guy, X1. And these are the values we use in the equation. Now, please look at the screen for a second. This is position 1, right? I'm just going to use black pens for position 1. In position 2, the disk, of course, is going to be in the same position, but rotating. The rod comes here. The sphere comes here. So you have center of mass for rod, and you have center of mass for sphere. That guy is going to come here, and this point is going to come here, right? So this is position 2. And meanwhile, this spring is going to be stretched more because it's going to turn around the disk. Okay. The first question is, because we're going to use energy anytime you have a spring and stuff like this, you're going to use work energy method. The first question is, do we have any non-conservative force? Yes or no? Someone?
No.
No non-conservative force. We have just gravity and a spring. If that's the case, there's no non-conservative force. And again, when we talk about force, is force, moment, couple, torque, any of them, right? Therefore, T1 plus V1 equals T2 plus V2. Okay. Because the problem says it's released, then T1 is equal to 0. When it gets to the point 2, it's going to have an omega 2. The whole thing is going to rotate with omega 2. So if that's the case, how much is T2? What kind of rigid body we have here? What kind of motion it has? Remember, you have 3 pieces welded together. So technically, this is your rigid body. If I can kind of. This is the rigid body, right? One single rigid body rotating about fixed point. This is your fixed point. Let's call it O. What is the kinetic energy of rotation about fixed point for a rigid body? You're going to get half IO omega 2 squared. Okay. Now we go with summation of V1s. We definitely have half K x1 squared. Also, as this system rotates, the center of gravity for some of them changes, so we have gravitational potential energy. How much is it in position 1? How much is the gravitational energy in position 1? Can I say 0?
That depends on the reference.
Exactly. I have to have the reference first. So let's go and select this line as my reference for Y, the line that goes through the center of mass for all of them. I mean, my plot is not as nice and accurate. Okay. This is Y, right? So if that's the case, then initial gravitational potential energy is 0. When we go to the final potential energy, this is spring. Look at here for a second, please, everybody. This spring is going to be a stretch because the end of it is going to turn around this, right? So there's going to be a larger x2, but we're going to calculate that later. Just know that you have half K x2 squared. And now the gravitational potential energy. I'll give you a minute to write this down, and then you can focus on the next part that I'm going to explain. Does the center of mass for this changes? Yes or no?
No.
For the disk itself, no. I already mentioned how the rod goes down. So the center of mass comes down this much, which is R plus L by 2. So for the rod, you're going to have mg m rod g. Your y, first of all, is going to be negative. I'm not going to make that mistake again. Minus. Then you're going to get R plus L by 2. That's how much the center of mass coming down for rod. Then it goes to the sphere. Look at here for a second, please. Sphere is here, right? And then comes all the way here, which means it's going to come down this much. This distance is R plus L plus R sphere. So you're going to get minus M of a sphere, G, R plus L plus R of a sphere. This is, when we say R, this is R for the disk. I think, yeah, I should use D here. Okay. So this is all coming together as V2. I'm going to substitute them in the equation before moving forward to make one simple equation. If I do that, on the left-hand side, I have half K x1 squared. On the right-hand side, half IO omega 2 squared, which is this term, plus half K x2 squared minus m rod G r disk plus L by 2 minus m sphere G r disk plus L plus r sphere. So this is the final equation, right? Let's see what we know and what we don't know. X1, I know. IO, I can calculate it. I'm going to calculate that, but it's a part of geometry. Omega 2, I don't know. X2, I have to calculate it. Then the rest is just numbers. Okay. So I have two parameters. Let's just highlight them by I have two parameters, IO and X2 to calculate. First, I'm going to go with X2. Remember, look at here for a second, please. Let's say the end of a spring is attached here, okay? As this rotates 90 degrees, your spring is going to be stretched an extra length of this much, right? When this goes 90 degrees, the end of a spring is going to be stretched this much. How much is this length? One-fourth of the perimeter, right? So your X2 is going to be X1 plus pi by 2 times R disk. And we can simply calculate this one plus pi by 2 times 2, I think the, yeah, it's 2 feet. So pi technically is pi plus 1, which is going to be 4.1416 feet. So I got this guy. How about IO? How do I calculate IO? I'm going to redraw the geometry, okay, here to see what kind of things we are dealing with. We have a disk. We have a rod. And we have a sphere, right? And I want to find I about O. So this is disk. This is rod. And this is a sphere. So if I want to find IO, it's going to be IO for disk plus IO for rod plus IO for a sphere. Right? Now, for the disk, this is its center of mass. So IO for disk is simple. Half M disk R disk squared. This is just from the back of the book. For the rod, you have to use parallel axis theorem because we know, look at here for a second, please, everybody. I know that for rod, I about G, its own G, I can calculate that, right? Is in the back of textbook. Then I'm going to use parallel axis theorem. This is going to be my D. So technically, this guy is going to be I of rod about G plus M rod D squared. And I for rod about G is going to be M rod L squared by 12. And this distance here is, look at here, this distance is R plus half L. So we're going to get M rod times R disk plus L by 2 squared. This is going to be the value for rod. So if I highlight it, I have this guy and I have this guy. Now I'm going to go for the disk, for the sphere. Let me give you a second to write this down. And then I'm going to go for a sphere. Any question about this? Any confusion? I'm using the parallel axis theorem. Do you remember which chapter it was? Chapter 17. Right? You can go back and look at this. Now I'm going to go to sphere. I about O for a sphere is going to be I about its own G plus M sphere its own D squared. For a sphere, this is center of mass G, and this is going to be your D, which is going to be R plus L plus R sphere. For a sphere, if you go to the back of the textbook, I about its center is 2/5 M R squared plus M sphere R disk plus L plus R sphere all squared. Okay. And this is the last part. So this guy plus this guy plus this guy is going to give you your final IO. I give you 2-3 minutes to calculate this and give me IO. And I want everybody to do it. Please, everybody, try this. It looks very simple and, you know, kind of boring, but plug in the numbers, you follow what is what, and it may bring some questions that I can answer right now. And I want to see who gets the final IO first. It's like a race or something. Anyone got the number?
I got 5.1655.
5.1655. Because I don't have, you know, the solution manual doesn't calculate this separately. They usually substitute all in one number. I don't know. So I'm going to wait for someone else to calculate this and see if it's the same. What's the unit, by the way? What is the unit for this?
Is it slug foot squared?
Yes. Anyone else get something similar or close?
That's what I got as well.
Okay, then if two people get the same number, I think we can trust. Because I never trust my own calculation. There's always, I make mistakes here and there, specifically using the iPhone. It's not actual calculator. Okay, we got this guy. Good. Now we have x2. We have everything. Let's just substitute the numbers here. I'm going to clean this part because I want to see what is what. Plug in all the numbers and see how the final equation looks like. So you're going to get half. And let me see what is the values here. Times 4 times 1 square is equal to half. IO was 51655. Times omega 2 squared plus half. 4 x2 is here, 4.1416 squared minus, remember, these are mg values, so I can just use the weight, okay? So it's going to be, for rod, is going to be 2 times 2.5. And for a sphere, it's going to be 10 times 3.5. In this equation, as I said, the only unknown is omega 2. And if you calculate that, and again, I'm going to give you another minute to do this. Please, everybody, try to do that. And your final omega 2 should be 1.73 radian per second.
I got the same number.
Okay, good. So, can you guys pause for a second, look at here, because I want to explain the whole process again. So in this problem, I think the physics wasn't complicated, right? Getting into this equation was easy, just terms, no problem. The only thing is it's complicated geometry, right? You had to calculate this displacement. You had to calculate I for this. Also, with again, use this arc as displacement or deformation for K. Technically, it's like R theta, and theta was 90 degree, right? So we experienced that again. If you add these things together, it looks a little lengthy to calculate all of these terms, but the dynamics part probably takes 2 minutes to write down. The rest is just calculations of moment of inertia, the lengths, all the dimensions and stuff like that. Does that make sense? So we practiced 3 problems of different sorts, right? You saw something with initial velocity like the previous problem. Like this guy had initial omega. You had something like this problem that has external couple as non-conservative force to calculate. You had the springs and gravity in all of them almost. So I think this gives you a range of problems. I'm going to post the homeworks for this tonight. I didn't post it before because I thought if you don't solve any examples, you're not going to touch it anyway. So you're going to get 5, 6 more problems to try. And I think that's it. Today is Wednesday. On Friday, we're going to start the final chapter. And the homework for this is going to be due maybe next Tuesday, Wednesday. As I said, we have to squeeze a little bit so we can give you the solutions. And on Monday, we're going to have a quiz covering chapter 17. Do you want to cover chapter 17 or 18 for quiz? Because I can give quiz 1 problem from one of the chapters. Which one you prefer? 17 was Newton's second law. 18 is work energy.
18.
How many of you want 18? 1, 2, 3. The rest don't care. Or some of you even don't listen, I guess. Kelly, 17 or 18? Because 18 is easier, you see, it's newer, but and you can finish the homework of 18 before 17, that's fine. Right?
When would the quiz be?
Monday.
I feel like I'd want 17 just so I could have the homework solutions.
How about this? Because we finished both chapters, if 18 is easier, I can give the deadline for homework 18 this weekend, post the solutions and give the quiz and give you a little extension for 17. Would that be better for everyone? Now, with this case, how many of you prefer 18? How many of you still prefer 17? Come on, guys, say something. Yoon. How is it? I think how is it? He says 18. You know what? You guys type in the chat which one you prefer, and I will pick that one, and I make adjustment for the deadline. Okay, I think everyone says 18. Let me see. I have 4 18s. Not everyone responded yet. Okay, 2 more. 6 18. Kelly, did you respond?
Yeah.
Okay, everyone. Okay, this is how we do it. I'm going to post the homeworks right after the class. The deadline is going to be Sunday midnight, what it was for 17. Okay? I switched the deadline of 17 to the Tuesday midnight. Okay? So we kind of switched the thing. And then on Monday, we're going to have a quiz covering chapter 18. Looks good? Okay. And this is recorded, so for the student who is missing the class, and I'll probably send this in an email, explain how things work for Aaron who wasn't here, right? And so we're gonna have a quiz covering chapter 18, and you should submit your homeworks by Saturday midnight, because Sunday morning I'm gonna post the solutions, okay? Is a good plan? Did you guys enjoy the lecture? Yes, no? You're too tired to respond? Okay, thank you very much. I'm gonna post the video for this lecture later today. I'm gonna post the homework and send an email about this adjustment we had. Yes, Colin, yes. Now, if you guys are done, you can leave. I have a student here want to talk to me or maybe ask questions. I'm gonna stop recording.